In this video, we take a look at derivatives of complex functions and we try to understand how it is defined and when does it make sense to talk about complex derivatives. So let's start with the very basic definition of complex derivatives. Suppose we have a complex function f of z, then its derivative is defined to be a function f prime of z, which is defined as at a point z equal to z0, the value is defined as the limit as delta z goes to 0 of f of z0 plus delta z minus f of z0 divided by delta z. And recall that this is very similar to that for real functions. So let's say you have a function g of x. The derivative at value x0 is defined to be g prime of x0, which is just the limit as delta x goes to 0 of g of x0 plus delta x minus g of x0 divided by delta x. Here the numerator denotes the change in g of x, while the denominator denotes the change in x. Similarly, for the complex derivative, the numerator denotes the change in function f of z, while the denominator denotes the change in z. Recall that the real derivative exists if and only if the limit as we approach from the left hand side, that is x0 from minus delta x, is same as the limit if we approach from the right hand side, that is from x0 plus delta x. And if these two limits are equal, then we say that the limit exists. That is, if the left limit is same as the right limit, then we say that both are equal to the derivative. Okay, so we have to follow a similar concept for complex derivatives. That is, this function f prime of z0 is well defined if and only if this limit does not depend on how delta z approaches 0. Okay, that is, it doesn't depend on which direction it approaches from 0. And for complex derivatives, the picture is much more complicated. So let's try to visualize this using the complex plane. Let's say the point z0, and for a certain value of delta z, z0 plus delta z is situated over here. But for a different value of delta z, z0 plus delta z can be in a different direction. Okay. And correspondingly, when we look at f mapped through these two, okay, so f of z0 is, let's say, the point over here, then for the first case, f of z0 plus delta z may be located in a different direction, and that is, when we go from z0 to z0 plus delta z, we go from f of z0 to f of z0 plus delta z in a certain direction. But for a different value of delta z, the transition may be in a different direction. So when we define f of z0 plus delta z minus f of z0 divided by delta z, this limit may actually depend on the direction of delta z. And this is what makes it so complicated, okay, or makes it different from real derivatives. Let's look at an example that would make it clear. So let's say f of z is the function modulus of z square. Let's look at f of z0 plus delta z. This is modulus of z0 plus delta z square. And let's assume that z0 is x0 plus iota y0, and delta z is delta x plus iota delta y. So we can write this f of z0 plus delta z in terms of these as follows. So fully expand out using the formula for the modulus, and we get this is equal to x0 square plus y0 square plus delta x square plus delta y square plus twice x0 times delta x plus y0 times delta y. And then further simplifying, we get modulus of z0 square plus delta z square plus twice x0 delta x plus y0 delta y. Notice that the first term is simply f of z0, which is modulus of z0 square, and then there are the other terms. So therefore, the limit, the function derivative is f of z0 plus delta z minus f of z0 over delta z. This is equal to simply modulus of delta z square plus twice x0 plus delta x plus y0 delta y divided by delta z. Now we are going to simplify this further by using the fact that z bar is equal to modulus z square. Okay, so this using this, star becomes simply uh, the conjugate of delta z plus twice x naught delta x plus y naught delta y divided by delta z. Okay. Now let's take the limit as delta z approaches 0 of this ratio. Okay. So this ratio therefore becomes limit as delta z approaches 0 conjugate of delta z plus twice x naught delta x plus y naught delta y divided by delta x plus iota delta y. Notice that the first term goes to 0 as delta z goes to 0, whereas for the second term both the numerator and the denominator go to 0 as delta z approaches 0. So it's in a 0 over 0 form. So we have to think about it further. Okay, let's look at the first case when delta z is simply delta x plus iota times 0. That is, all the change happens in the real part. Okay, so if z0 is over here, then z0 plus delta z is a horizontal shift. So it's a horizontal change in delta z. In this case, this ratio, or the limit of the ratio, simply becomes limit as delta x goes to 0 of twice x naught delta x plus 2 times y naught times 0 divided by delta x plus iota times 0. Okay. And further simplifying, so this is equal to twice x naught. Okay. Similarly, for the case when all the changes happens in the vertical direction, that is delta z is simply delta y times iota, we can perform the same calculation. Okay, and then this becomes limit as delta y goes to 0 of simply 2 times y naught times delta y divided by iota delta y, which is minus 2 iota delta y, minus 2 iota y naught. So the first one is the horizontal limit and the second one is the vertical limit. And notice here that in general the horizontal limit here, which is equal to twice x naught, this is different from the vertical limit, which is minus 2 iota y naught. And unless, of course, when x naught and y naught are both 0. This means that f of z equal to modulus z square is only differentiable at z equal to 0. Okay, notice that this is very different from the real case when gx equal to x square is differentiable everywhere. Okay, so this definition of complex derivatives, we have to be very careful because we have to make sure that the limit does not depend on how delta z approaches 0. And this property makes it much more complicated to define complex derivatives and to make sure that they exist. Okay, so in the next part of this video, we are going to look at a condition which characterizes when complex derivatives exist, and these are called Cauchy-Riemann equations or Cauchy-Riemann conditions, and they are an easy way to check if f prime z is well defined, that is, the derivative exists. Okay, so what are these equations? So these are some equations that tell us that if these are satisfied, then and only then the limit of f of z naught plus delta z minus f of z naught over delta z does not depend on the direction of delta z, and when it does not depend on the direction of delta z, it means that the limit exists. And in this course we are going to look at a specific kind of Cauchy-Riemann equations which guarantee that if these equations are satisfied, then and only then the horizontal limit is same as the vertical limit. Okay, so let's consider a general function f of z equal to uxy plus iota vxy, where z is equal to x plus iota y. Let's first evaluate the horizontal limit of the derivative, okay, at a point z0. So this is defined as the limit as delta x goes to 0. Okay, notice that z0 is going to z0 plus delta x because we are only looking at the horizontal limit. Okay, so the derivative then becomes limit of f of z0 plus delta x minus f of z0 divided by delta x, and this can be written in terms of the functions u and v as the change in the function u as xy goes to x naught x plus delta x comma y, and the change in the function v as you go from xy to x plus delta x comma y. Okay. Notice that in both of these terms only the x argument changes, okay, and we are looking at the rate of change with respect to just the x argument. Let's take a quick detour and remind ourselves of partial derivatives. So for a function u, we say that the partial derivative of u with respect to x is simply the rate of change of this function when you change the x coordinate. So therefore, the the limit of the derivatives in the horizontal direction simply becomes the partial derivative with respect to x of u at the point x naught y naught plus iota times the partial derivative with respect to x of v at this point, and this is we'll write as ux of at x naught y naught plus iota vx at x naught y naught. Similarly, we can calculate the vertical derivative. Okay, so that is, we want to look at the ratio f of z naught plus iota delta y minus f of z naught over iota delta y, and here we are changing from z naught to z naught plus iota delta y. That is only in the imaginary part or in the vertical direction. In a similar way, we can write this in terms of the rate of change of the function u plus iota times the rate of change of the function v when we go from x naught comma y naught to x naught comma y naught plus delta y, and this can further be expressed in terms of the partial derivatives as 1 over iota uy of x naught y naught plus vy x naught y naught, and 1 over I is simply minus iota, so you get minus iota uy x naught y naught plus vy x naught y naught. So the first term, the first thing we calculated was the horizontal derivative, and what we just now calculated is the vertical derivative. Okay, and we said that fz is differentiable, then the horizontal derivative should be equal to the vertical derivative. Okay, in other words, both the real and imaginary parts of these should be the same. Okay, so matching the real parts of the horizontal and the vertical derivative, we get ux of x naught y naught is equal to vy of x naught y naught, and vx of x naught y naught is equal to uy of x naught y naught. And these two conditions are together called the Cauchy-Riemann equations or the Cauchy-Riemann conditions. And so what we just saw, this shows that if fz is differentiable at z equal to z naught, then Cauchy-Riemann equations must be satisfied. Further, we can also say the following. If fz is differentiable, then the horizontal derivative must be equal to the vertical derivative. Then in order to calculate the derivative, it's enough to look at the derivative in any direction. In particular, you can write it out in terms of the horizontal derivative, that is ux of x naught y naught plus iota vx x naught y naught, or you can write it in terms of the vertical derivative, which is vy x naught y naught minus iota uy x naught y naught, and both are going to be equal, and both are equivalent ways of calculating that expression for the derivative. Let's look at an example to see how to use this. So let's say fz equal to z square. Okay. First we want to answer, is fz differentiable everywhere? If so, we want to find what the derivative is. Okay. So let's first write z as x plus iota y, and let's write fz in terms of the real and imaginary part. Okay. So the real part uxy is simply x square minus y square, and imaginary part is 2xy. Okay. If Cauchy-Riemann equations are to be satisfied, then ux is equal to 2x, and notice that this is same as vy, so the first Cauchy-Riemann equation is satisfied. Similarly, vx of xy is the partial derivative with respect to x of this function v, which is equal to 2 times y, and notice that this is the same as the derivative of the function u with respect to y multiplied by minus 1. Okay. So both the Cauchy-Riemann equations are satisfied, which means fz is differentiable, and since both equations are satisfied everywhere on the complex plane, this means that fz is differentiable everywhere on the complex plane. Okay. Now, if this is the case, we can write f prime z in terms of the horizontal derivative. Okay, so ux plus iota vx, and you can see that you can perform this calculation and you get this is same as twice z.